Okay. Beautiful. Okay. So as we get started here, I'm just going to go ahead and pop in the room, make sure people have the content. So we'll have a moment or two of just getting things acclimated. Let's see. Okay, just waiting a minute here. It's 11:03 a.m. for people from the class to hop in. Okay, great. Looks like people are getting into the link. So if you're popping in right now in the Hangout, I'm also monitoring the chat room. Just want to know if the Hangout is working. Awesome, great. So we're going to give it like 2 or 3 minutes and then I'll get into it. But I did share the slides and the repository, which just has the 4 problems with both an iterative and a recursive solution that we'll talk about after we talk about what recursion is. So if you don't have those materials, just feel free to ask in the room. I'm going to kind of pause every few minutes, make sure things are looking good. And as you have questions, I'll do my best to try to vet that. So let me know if there's anything in between that you need. And like I said, let's just give it another minute or two. This is my first Google Air Hangout, so I feel very omnipotent. Okay. For people who are in the room, just, oh goodness, my email client. I thought it was on Do Not Disturb.
Got this other website for the chat.
Okay, great. And I think for people who are in the room, if you would like to mute yourself, that would be ideal because I can hear some of the background noise. Okay, great. Thank you, Kira. I appreciate it. Okay, great. So thank you so much for being patient. I'm going to go ahead and get started. So for those of you who don't have the slides, I've already shared it in the room. If you don't have that, just ask again. I'll reshare them again right now. And let's go ahead and get started. So bear with me for a moment. I'm just going to be pulling up the slides real quick. Okay, great. So right now, I won't be able to have the view of seeing what's going on in the chat room. So like I said, I'll try to pause every few minutes and back up a step if people have questions. That being said, we will have a few TAs who'll be popping in, so feel free to have a conversation in there as well. Okay, great. So yeah, thank you so much for joining me today. So today's class is called From Guess and Check to Recursion. So just a quick little introduction about kind of where this class came from and why I thought this might be something worthwhile. So PyLadies Remote is a brilliant organization. They just in July, I believe, had their first class, which was going to be Python 101, you know, just a soft introduction to basic primitives, what is Python, what are good ways to figure out libraries you should use, and what are some good learning resources to help you after the class. So while the classes aren't per se going to be successive with one concept leading to the next, I thought this might be a nice little introduction talk for people who are just getting into maybe programming, or for people who are just starting to make their way through Python and are perhaps curious about some of the concepts and what they look like in Python. So my name's Lorena, and I am a co-organizer for PyLadies Chicago. And actually, in the discussion with our own community, some of these concepts have been bubbling up to the top. So this was something I was working on independently, and thought, let's give it a chance. Let's give it a shot at PyLadies Remote and see if we can get some good conversation around this, and perhaps some recommendations for future projects after this class. Okay, great. So we're going to start out with a little thought experiment. So let's think a little bit about a palindrome. Let's say I want to know I want to be able to figure out if a word is a palindrome. How may I be able to figure that out? Well, the first thing we want to think about is, well, let's break down what is a palindrome. So I like the idea that you know it when you see it kind of thing, but what we're trying to do is we want to move past that knowing it when I see it and really have some definitive words to describe the problem that we're solving, just like anything you do with programming. So with a palindrome is a word that is spelled the same left to right and right to left. For example, a race car is the same left to right and the same right to left. Okay, so now that I know what a palindrome is, that's going to be my end goal. It's to find a word that reads the same left to right and right to left. Now let's break that down into some steps. So we're going to do a little pseudocode. So the idea so my word is actually a collection of letters. So what I would like to do is look at each unit in the word, so each letter in the word, reading left to right, and I'm going to be asking this question. Is the nth letter equal to the negative nth letter? So for example, if we're looking at race car, I would say, is the first letter to the negative first letter in race car? And I'll do this for each word, or for each letter in the. So I ask the question, is the nth letter equal to the negative nth letter? And I have two options, either yes or no. So in the case yes, the letters are equal, I'm going to continue on. If the case is no, the letters aren't equal, I'm going to stop, because right away I know this word is not a palindrome. After I've looked at every letter in the word, if I haven't reached a fork in the road where I say no, these letters are not equal, then we can definitively say yes, this word is a palindrome. Okay, great. So now that we know what is our palindrome, we have an understanding of what our end goal is. That is to just say yes or no, this word is a palindrome. We know how to map that out. Now let's go ahead and put some code into it. And now I'm going to switch over to some code that I have in CoderPad. Okay, so I'm going to be using Python 2 today. And for those of you who have seen the repository, all these problems are in there, and basically the idea is let's write the solution first with an iterative solution, and then let's write the solution with a recursive solution. So the first thing we will want to think about, if we are back to our pseudocode, is we want to be able to look at each letter in the word. Okay, so this is easy enough in Python. We can easily use a for loop. So the method I've opted to use is enumerate. What enumerate provides us is it's going to give us two pieces of information, both the index of the thing I'm currently looking at and the element itself. Since a word, if you think about it as a list of characters, we can then understand that this is actually a collection, something that we can apply an iterator to. So line 13, I'm just going to go ahead and say, okay, so for each index and character in my word, if the index is equal to 0, then the right to left index is going to be equal to -1. So this is a little bit of this is kind of the unique case, since the way to read values right to left in a string for Python, you have to use, you don't start at 0. The only time 0 is applicable is the first element that's going to be left to right. So that's going to be our one unique case. So the first time I start, I say, okay, if the first letter that I'm looking at is If it's the first letter I'm looking at, then its equivalent pair is going to be the negative one, because again, lists are zero based. So let's say we are starting with civic. So I'm on the first letter, and reading left to right, my index is provided by the enumerate. If I'm reading right to left, I have to manually create that index to find the last letter, which in this case, if index is equal to 0, right to left index is -1. So what I'm saying here, and there's a little bit of manipulation on my part here, I'm just being a little safe and saying, hey, if whatever element I'm looking at is capitalized, let's just go ahead and lowercase it. That way, you know, the only thing we care about in our definition is that the letters themselves are the same. It's not case sensitive in this context. So I say if the first letter reading left to right is equal to the -1 letter right to left, if it is not equal, then we're going to go ahead and say let's just fail fast. This is not a palindrome. Otherwise, I'm just going to continue to iterate, moving left to right, and then comparing it with its equivalent pair right to left. So we do this for each letter in the word, and if I don't hit line 16, then I'm just going to return true. So this is a pretty straightforward implementation. Nothing too crazy here. And just to kind of show you that it works, I've put some test cases here. We've got civic, we've got mom, we've got reviver, race car, redivider, car, and civics. So we have two cases, lines 30 and 31, that we don't expect to be true cases. The car is not spelled the same left to right as it is right to left. The same with civics. So let's go ahead and check that out. Okay, cool. So it looks like my base case is passed. So you might notice on line 32, I've got a commented out case here. I could perhaps adjust my code to work with an entire phrase. So for example, this is one that's supposed to be a palindrome phrase, left to right, right to left. Notice there's some spacing and punctuation in it. And while I have adjusted for capital letters, I would have to do some logic to take care of spacing and punctuation. But I'm not yet doing that, so that's just something that, should you want to go the extra mile, that's the case. But in this definition, we're just looking at a word itself. Okay, great. So we've got some base template language here, and we've got a solution that works. So let's break that down a little bit. So I'm going to pause, and I'm going to look first at the room and see if anyone has any questions. That is not the room. Here we go. Okay. Nope, we look good. Okay, great. So let's go ahead and go back to our slides. Okay. So we've seen an iterative solution that exemplifies this pseudocode. We've coded it, and we've got a working solution. Granted, so I have a note up there that I could rewrite this as a while loop. There's quite a few ways we can do this, right? So if I were to write this as a while loop, I could say while the nth character is equal to the negative nth character, continue to look at each character, reading left to right, right to left, something to that extent. So let's break down a little bit what we did in this approach. So in this approach, we're kind of making use of this guess and check mechanism. That is, each time that we're looking at the characters, we're using our best guess to determine if the word is a palindrome. We're saying, hey, is the nth letter equal to the negative nth letter? This is just a quick way for us to make a guess for what we understand a palindrome to be. And based on the outcome, it's either going to tell us yes, we can continue to guess the word is a palindrome, or no, it isn't. You may hear a term called exhaustive enumeration. This is something that this style of approach is kind of simulating. The idea that we're generating every possible scenario to understand to understand in this case if the word is a palindrome, and that is the pairs of all the characters reading left to right and right to left, to see if all the pairs are in fact equal. So the best way we can think of guess and check is we check every possibility until we find the answer we're looking for. So if the first way we can do this is by doing exhaustive enumeration, listing every possibility until we've run out of possibilities, what's another way we can do this? Okay, I thought this was pretty silly. So surprise, surprise, recursion is another way that we could go about solving this problem. So for those of you who have perhaps not seen this before, this is a great little Google Easter egg. So if you were to type in recursion, it gives you a suggestion that what you're looking for is recursion. And here's a little hint of what recursion is: the idea of a repeated application of a recursive procedure or definition. Don't worry, we'll have a better definition that does not use the word recursive in it, but you can see that there's something to be said about repeating itself. That's what recursion talks about. There's some kind of repetition in the procedure you're doing, and Google here, tongue-in-cheek, is demonstrating this repetition by saying, hey, did you mean this? When actually we had typed the word that we were looking for. So the repetition there is a fun little joke. Okay, so let's think about recursion. So recursion, we can think of it as a way for breaking a problem apart into a series of smaller problems. So the first step that we really want to do is we want to reduce the problem into a simpler set of problems. These smaller problems are of the same type of the original problem. So the idea of reduction into a smaller series of problems that are of the same type as the parent problem. Okay, so that's great. What does that actually mean? Well, one way we see recursion used very often in programming, it's used in divide and conquer problems. So when we talk about divide and conquer algorithms or problems, divide and conquer algorithms solve a problem by breaking it down into smaller pieces. We keep doing this process of reduction until we reach a point in time where the problem's been reduced so much that it's really simple to evaluate and solve. Once we've solved all of these smaller problems, we can combine the results of all the smaller problems together to produce the result for the original problem. So, you know, the idea of reduction, if you're a Star Trek fan like me, the idea of reduction, it's kind of that effect of looking into the mirror and you see all the mirrors behind you and you can have that endless series. The idea is you're trying to understand the problem in its simplest form. So really concrete definitions to have a simple, and that's great. We know we want to divide this problem up somehow, but what exactly does it mean to have a simple enough problem to solve? Okay, so the big thing with recursion and the way we implement it in programming is we have to have some way to evaluate a simple enough stage. We can now directly solve this subset problem. So the way we do this is with a base case. This is a point at which we stopped the division of the problem into smaller subtasks, and this is a point in time when the problem can be directly solved. The idea of what a base case is and how it will look, it's really going to differ depending on the problem solved. But there is this idea that you need to have criteria for evaluating when you stop this division process, and that's going to be the base case. So let's think about a different example this time. Let's say if you're anything like me, I'm terrible with directions. So let's say you're like me and you need to find your way home. How can you go about doing it? So let's think about when you know you've actually reached home. Well, you know you're home when you're actually home. You can stop trying to figure out your way home. So that in this small example, we'll say that's our base case. If you're at home, stop moving, you're home. So that's great. That's going to be the way that we say, okay, stop, you're done. You don't need to do anything else. But how do we get to that point? Well, the way you may think about going home is perhaps you take one step toward home, or you walk 1 mile and then you stop and reevaluate. So the idea here is there's a set of instructions you're going to execute over and over. You'll do these set of instructions at the end of the instructions you've defined for yourself. You then ask yourself, is the base case applicable? So let's think about that. I'm lost. I first ask myself, hey, am I home? No, I'm not. So what should I do? Step 2, I'm going to take 1 step forward towards going home. So I'm dividing the problem up by actually taking some action. Then the third thing, I have some metrics for finding my way home. So maybe the repetition here is I look at my phone on Google Maps. I ask someone who's right next to me. There could be a few ways to do this. Maybe the simplest way is look around, see if there's someone by me, and I can ask them which way to go. So I ask for directions. I then reevaluate and say, hey, am I home yet? If I'm home, stop moving. If not, take a step forward, look around, ask for directions, and keep repeating that process. So while this is a little bit simplistic, the idea here is you want to kind of think of it, you want to think of your problem in three ways. You know, what's gonna help you actually make the problem simpler? What's gonna help you actually solve the problem? And then how do you know you're done solving the problem? So to reiterate, the base case is going to terminate the recursive call and allow us to solve a problem. So in a recursive algorithm, so we've talked a little bit about a base case and what that may look like if you were trying to find your way home. Well, let's go back into thinking about algorithm design. In our algorithms, the way that we'll want to start, there may, again, depending on the problem, you might have to kind of manipulate this. So when we start our algorithm, you may need to seed some initial value. We'll look at an example that talks about this, but there may be something, you might have to start with a certain certain value in order for you to apply this replication process or this division process. So step one, we initialize the algorithm. Step two, check if the current values being processed match the base case. So back to going home, you know. If I'm going home, I want to say, hey, am I home? And my base case was, yes, you are home, stop moving. If that's a match, then we can say, okay, I'm done. I'm just going to return the value, yes, I'm home. Or if we're thinking about our palindrome problem, we can say, okay, my base case is maybe I have no characters left. I've already looked through everything, and everything has matched. I have nothing left to determine. I'm at the end of the word, so I can just return true. So we need some way of understanding when we are done. So that's going to be our base case. So check whatever value you're currently processing, see if it matches your base case. If it does, evaluate and return the value. Step three, if the base case doesn't match, then you'll need to redefine the answer in terms of a smaller or simpler subproblem or subproblem. So step one, start the algorithm. Step two, see if the base condition or the base case matches. If it doesn't, step three is going to be the division. The division. You're going to have some procedure for dividing the problem into a smaller problem. Step four, whatever the instructions are that divides the problem up, you're actually now going to implement them, which is basically going back to step two, step three, and you keep repeating that until you hit your base case. So step five, once you've solved all the subproblems, you'll combine the results of all the subproblems to step six, return the final result of your problem. Okay, so we've got a little bit of a format here. Still probably is a little murky. I'm going to pause and look at the room and see if anyone has any questions. Yeah. Okay, doesn't look like there's anything yet. Okay, great. So let's go ahead and move on. Okay, so let's go back to palindromes because we love finding palindromes. We want to be able to know if race car is the same left to right as it is right to left. We really care about this. Okay, so let's rephrase this problem in the language that we've been talking about. Base case, division, and the repetition process. So what does it mean to divide our problem up into smaller problems? Well, we've been doing this actually with the iterative solution, which is we want to divide our word into pairs of the nth and negative nth letter. So that's going to be the way that we can take the idea of the entirety of the word being the same left to right, right to left, and now we've reduced it to a simpler, the scope is simpler. It's now just a pair of two characters that have the same position left to right, right to left. So our base case is going to be, is the size of the nth letter and negative nth letter pairing less than 1? That is, do we actually have enough letters to make a pair? If we don't, we've reached the end of our ability to compare the letters. The word has been completely compared. And now the evaluation step. Are the nth letter and negative nth letter the same? So that's a pretty straightforward yes or no. There's really no other way around it. And then the combination. So you've divided the word into all these pairs. Once you reach that base case that you have you're no longer able to make pairs, now you can evaluate each pair, and you can combine the results of all these pairings and say, well, hey, do all the pairs actually equal? If they do, we have a palindrome. If they don't, it's not a palindrome. So let's go back to our code. So now we've talked a little bit about this, and let's see how that would look in code. Okay, great. So I'm going to try to make this a little bigger. It might squish over, but for those of you who are following along, you can definitely look at the GitHub has the same solutions on it as well, and we'll be looking at it in the slides in a moment. So let me clear this output. Okay, great. So let's take a look at the recursive is palindrome. And actually, before I run the solution, I've got a good slide that breaks this down a little bit. So let's go back to this. Okay, so we've outlined the different components we'll need to put into our recursive solution. Now let's put this in pseudocode. So step 1, let's start with the base case. Is the size of the word less than 1? If yes, stop, return true. Evaluate. Is the first letter and the last letter of the word the same? Divide. Let's repeat the procedure with the balance of letters to be compared in the word. And then combine. Let's see. Let's combine all the results for the original evaluation. So to kind of speak this back, the way that this is going to work, we're going to start with our base case. We say, hey, is the size of the word, or in our case, is the size of the pairing that we're looking at less than 1? If it is, return. If it is, stop, return true, evaluate. If that's not the case, so base case is not applicable, now we want to look at what's left in the word and say, okay, cool. What in the word is the nth character equal to the negative nth character? So this is going to always be the first letter and the last letter of the word. If that is indeed the same, then we will go ahead and continue to divide. So if you can imagine race car, we're going to start by looking at index 0, index -1 of the word. Base case is not applicable because the entire word that we're still processing is race car. So that won't be applicable. We'll move to the evaluate step. We'll say, is the first letter equal to the last letter of the word? So is R equal to R? Yes. If that is true, we now know that we've processed that first pair, and we're gonna move in, and we're gonna look at A, C, E, A, and we're gonna look at basically the balance of the word minus the first R and the last R in the word, and we're gonna feed that back into our method, and we're gonna ask, is our base case, so is the size of the word left, is the number of characters left in the word to process less than 1? If yes, we're done. Otherwise, continue this evaluation of looking at the first character and the last character and continue to evaluate. The actual answer is going to be the combination of all the processings of pairs that we have. So let's actually break that down now in the code. Okay, so we kind of looked at this a little bit just for a second in the coder pad, but this, I think, breaks it up pretty nicely. So something you'll notice right away in a telltale sign that you're working with a recursive solution is you're actually going to see the method itself called within the body of the method. We call this a recursive call. So in this example here is palindrome. We have our base case, that is the size of the word that we're still processing, or the characters left in the word that we're processing. Is it less than 1? If so, if we have no characters in our word, there's nothing left to process. We're done, so let's return true. This is going to allow us to break out of the recursive call. If that's not the case, then now here comes the evaluate step. So first thing we do, we look at the first character, the last character, we test them in equality, and then we make a recursive call. So here's the replication, the division process. The evaluation is looking at the pairings, that is the nth and negative nth character, and then the division step is going to actually be taking the balance of the word that has yet to be processed. So if you notice, word is going to take the first index up to and not including the negative one index. We're going to pass that back into the method, and we're going to divide the problem up so that we can keep looking at the first and the last character in our words. So each time we come through this process, we first say, okay, do we have less than one characters in our word to process? Yes or no, because that's going to tell us if we're done. If that's not the case, then we're just going to keep kind of pulling off these pairs, seeing if they're equal or not. Once we've reached the end of the word being processed, we return true. And basically this return statement, where it says return, does the pair equal the pair, does the pair equal the pair, we're going to have the combination of all the pairings that's going to be in that return, that final return, and the combinations of if all those pairs are equal or not, plus the true when we reach the end of the word, is either going to tell us the word is or is not a palindrome. So still probably a little much. So let's actually look through the method calls. Okay, so this is probably a good. So this is a little. There's a lot on this screen. I did my best to kind of try to break it up a little bit. One thing I like to do when I'm working and I'm trying to understand what's going on with recursion, I like to actually take pen and paper and make a little chart. So for all my parameters, I'll put them on the header, and then on the left-hand side, I'll write the number for the method call, and then I actually trace it through so I can understand what's happening at each step of the process. So this is a little bit of my pen and paper mechanism just translated into a little bit more succinct form. So let's think about the word race car. So in the word race car, the word being processed as race car. Is the length of race car less than 1? No, it is not. We're good to go. So the base case isn't applicable, so we move to the else statement, and remember the first part of that evaluation step is going to be take the first character and take the last character and compare them together. If they're equal, we'll evaluate that at some point, or they're not going to be equal. We do a simple equality test with the is equal operator. So that's going to be our first layer of evaluation. Now we're going to divide up the problem. So what do? We take the first index of the original word race car up to and not including the -1 index of that word. So that's going to mean ACECA. So we're going to have ASCA, I think is how you say it. So we'll pass that in as the new word to be evaluated. Again, we're feeding it right back into the same procedure that we've written, the recursive procedure. So we ask the same question. Is the base case applicable here? Is the number of characters to be processed in the word less than 1? No, it is not. So let's go ahead, look at the first and the last characters, and let's do the division process again. So you'll notice we do this all the way down, all the way up to where it starts to get interesting is method call 5. So we've moved to the point where our pairing is E equals E. So on method call 4, if we were to take the first element up to the up to and not including the -1, well, we're not going to actually get anything. We'll be passing nothing in. So for method call 5, is the length of the word less than 1? This is going to be true finally. We have nothing left to process. So we don't actually do the division step. We skip over it, and we just move on. We just return true. So method call 5 is going to return back to the scope of method call 4. So this is, you can kind of think of it a little bit like you're building a pyramid, but it's inverted. You're funneling down to a smaller input, and then you move back up the method call chain. So method call 5, we've returned true, so we move back up to method call 4. So now we can actually return the result of the comparison operation of E is equal to E. Well, true plus true equals true. The right-hand side of that comparison true, that is the result of method call 5. If you were to look at the code again on the else statement, when we break up the pairings, it says plus recursive call word of 1 up to -1. That's going to be always like what you see on the right-hand side of the operation. That's going to be the result of that. So you can see we move from method call 4 all the way up to method call 1. And eventually then we get to the place, hey, is R equal to R? Yes, it is. And true plus true is equal to true. So that's good. So another way perhaps you can think about it, if you're anything like, if you're a fan of looking at things perhaps all at the same time, you can also think of this a little bit like order of operations. It's kind of like I've rewritten the method calls beneath to kind of read as order of operations. So in this context, start with the innermost parentheses and evaluate from the inwards out, right? So the 5th method call results in true because we no longer have any words to process. So we've evaluated that, and then we can say is E equal to E. That's the last pair, the 4th pair that we make from our palindrome, and then we keep working from inwards outwards until eventually we have the result, which is true. Okay, so just to prove this works, I'm going to go back now to the coder pad, and before I do that, let's pop in the room and see if people have questions. Okay, cool. I will try to make my screen bigger, and sorry about that. In regards to the code on CoderPad, that's going to be the only place I have control over that. The Google Slides, it's already in presenter mode. So if you're having a little bit of a hard time, let me do, did you see the link for the GitHub? It also includes the problems I'm going through. So if you were to go to the palindrome one, I've got it all right here, so we can do that. So let me just copy this back in the room. Okay, beautiful. Sorry about that. I'll do my best to try to make it a little bigger in CoderPad. It's a little hard because I've got the output on the right. Oh my goodness, I'm sorry about my email client. I thought I had to not disturb. Okay, let's go back now to the CoderPad. Okay, cool. So so this is now, so we've got our code again, and just to kind of confirm that we've done what we think we've done, here's our same test cases. So again, we have 2 that we expect to be false. So car is not the same left to right as it is right to left. And civic, well, civic itself is a palindrome, civics is not. So let's go ahead and try this out, and things look good. So if we were to, again, rephrase and break up this problem for the components we're looking for, here's our base case, here's our evaluation step, and then here's the division part. And by division, when we're thinking of divide and conquer, this is the divide part, and the conquering is just more or less doing the recursive calls. It's allowing you to do a little bit more work with a simpler procedure. So that's the body of this. If you were curious and you wanted to do phrases, something that you could do to let's say, to process this phrase where it has a bunch of names, and I guess all these people sinned. I pulled this off Wikipedia, so that's these people are not good. So kind of like I said again, and actually what I did in the iterative solution that I didn't really carry out here, you could, when you're looking at the word, you can lowercase it all, which would be ideal because if you're thinking about the kind of the purest form of a palindrome, it's just that the characters are the same left to right as they are right to left. So you would want to lowercase them, and again, you could for processing a phrase, you could, anytime you see a space, you can replace it with no space, and every time you see punctuation, in this example here, I just did a comma, you could replace it with nothing. So if you had a phrase where you wanted to strip out all the special characters perhaps and just look at the characters themselves to see if it's a palindrome phrase, you could do all this kind of simple replace logic to remove the special characters and just insert nothing in its place. So yeah, that would afford you some of that. But anyway, so let's continue onwards. Okay. And awesome. Okay, let's get back to it. And alrighty. Oh, that's the wrong size. Sorry about that. View. No, I am silly goose. File, view, exit presentation mode. All right, view, there we go, present. Wrong presenter mode. Okay, so we walked through one example. We've talked a little bit about how the method call looks. But I'm sure if you're like me, like if this is your first time looking at a recursive solution, there's a lot going on. It's probably difficult to keep track in your mind. So while writing things out can be helpful, maybe it's a little bit easier to help visualize some of this. So let's think a little bit actually about what the computer does and how that works. You know, in my brain, I think of it gets a little sticky. So something about how does this magic work? Basically, every time you call the function again, every time you have that additional function call, what the computer does is it's storing that value in the call stack. So if you've heard of stacks before, great, that's what we're using. If you haven't, stacks are a data structure that operate last in, first out. So stacks can also be first in, first out, or queues rather can be first in, first out. First in, last out, my bad. But stacks as a data structure operate in last in, first out. So if you were to think about last in, first out, back to our method calls here, the last method call in is method call 5, the point at which we've processed all the characters and we have nothing left to process. So once we've gotten to the point that we actually can return something from the last method call, that's going to be like the first thing that's taken out of the method, out of the call stack. So method call 5 is going to, since it's the last method call in, it's going to be the first one that's taken out of the call stack. So let's think of it a little bit more graphically. So let's say that A is method call 4 and B is method call 5. So what this is showing you down here, the previous contents, basically that's, you know, method calls 1 up to method calls 4. We don't process them until we get to that last thing. So whatever's the last thing to be processed. So in this case, the point at which word is equal to an empty string, that's going to be the last thing to process because we return true. We break out of the scope. We don't make another recursive call. So method call 5 is going to be represented here as B in the graph. And since the stack is last in, first out, we evaluate it and we pop it off the call stack. So then we go to method call 4. In this context here, we evaluate it, we pop it off the stack. And then we keep going on and we evaluate the previous contents, which would be method calls 1 up to method calls 4. So it's a little interesting to think about, but you can kind of think of it as like the idea of a pyramid, right? You have the largest the stack will be that base layer. That's when you have until you reach the base case, the stack call is going to grow, and once you reach the base case and you break out of the scope, you no longer make recursive calls, you're going to then move into the pattern where you're evaluating the successive method calls and popping them off the call stack. Okay, cool. So let's just check and see if anyone has any questions. Otherwise, we're going to spend a few minutes and we'll wrap up doing a few problems. And some of these are relatively straightforward. We do binary search, which I think is a good one. But yeah, we'll look at that in a second. Okay, cool. So I don't think anyone has questions, so I'm glad to hear it. Okay, great. So let's go ahead and do some more coding. Okay, so recursion, let's try that again. Okay, so this is a good one, and actually this is one I kind of like a lot. So let's flatten a list. So the idea here would be you have, let's say, a list that is made of numbers and made of other lists. But what we want is we want a one-dimensional list. So how can we dimensionalize? I just mean everything in the list is, in this case, going to be integer. So let's think a little bit about that pseudocode. Let's in the in the idea of flattening a list, where again we want to look at each unit and the thing being processed. So in this case, we want to look at each element in the list as we process the list. If the element itself is a list, then we want to repeat some kind of process, which would be, okay, we want to go into that list and we want to say, hey, is each thing in this a list or not? We'll come back to this repeat process in a second, but back to this initial question, is the element a list? Why do we care about this? Well, the reason we care about this question is because if you don't have, if the element you're currently processing and looking at, if it's not a list, we don't care. We're done processing that element. So we can just add that element to a new list and move on. If it is a list, then we need to do something different. So this repeat process part, that's kind of what we have to figure out. That's going to be the meat of our division, if you will. So the way we divide the problem up is we want to move to the point where each element in the thing we're processing is itself a unit that is not a collection, is not a list, and that's going to kind of guide our base case. You know, is everything that we've looked at already been processed? Have we processed everything to the point that it is no longer contained of collections of things? So let's pull that up a little bit. So I'm going to actually pull up some of my code here. So the flatten. Okay, cool. So let's start with a iterative solution. Okay. The idea here, the scope of our problem, we want to write a program that uses iteration to flatten a sequence type. So, you know, list, tuple, perhaps maybe you could do some others, but we'll just start with that. And we want to flatten this sequence type into a one-level sequence type, so one-dimensional, something to that effect. So if we were to do this iteratively, again, we can use our enumerate method, which is lovely. It provides us the index and the value. And we want to iterate over the items being processed, and we ask that question. Hey, you know, is this item that we're looking at, is it itself a collection? So while the instance is a collection, then we want to go ahead and look at all the smaller units and make sure that we don't make sure we reach the point where the items itself are no longer a collection type. Once we've kind of exhausted these set of instructions for each element in the initial items that we're processing, we can go ahead and return this. So the thing that gets a little expensive here, right? We're iterating over an original list, but once we find a situation where the item itself, so we're looking at items, index, probably could have used val here, but when we see that the item itself that's being, the current thing we're looking at, when we see that it is either a list or a tuple, then we're going to go ahead and we're going to pull off all the items off of the value, and we're just going to stuff it into items. So we go in, we pull everything off, which is fun. Okay, cool. And just to see that this works, let's go ahead and run that. So if you've not used Sublime Text, I'm being a little lazy and just building it here, but for the case of keeping everything in one screen, our simple little case works. This evaluates to a flattened list of 1, 2, 3, 4, 5. Okay, so we know that the way that we'll break the problem up is we need to know if the item is a list or not, and then we're going to have some kind of way of pulling all the things out, and that's going to be when we can directly solve it. Basically, we get to the point where we have a list, and we're going to have to pull stuff out, and then we can add it back to a new. List. Okay. So something I kind of don't like about this, reading a for loop with a while loop in it can get a little, I feel, asks you to keep track of a few things in your head, and then imagine if you had like another nested iterator, once you're iterating, once you have nested iterations, that can become an expensive computation, or at least just reading it, it can be a little difficult, I feel. So let's see if we can kind of apply this with a recursive solution. And so the idea of a base case, right? We want to say, have we processed everything? And then also the idea also then of a way we can divide the problem is we need to have a way to divide the problem. So in our case, base case, it's just going to simply be we processed everything in the sequence type. Because once we've processed everything, we know we're done. And then how do we do the division? Well, we're going to use the case of, is the element being processed of type seq type, of type list or set tuple? If so, if yes, then we're going to repeat this. We're going to repeat this process. Otherwise, if no, we're going to take the thing being processed. We're going to add it to a new list. So the idea here is we want to keep going into each successive list that we find so that we can pull it out into a new flattened list and then do something with it. And that do something with it is going to be a little interesting. And part of the magic here is going to be understanding how you can do addition with lists. So I think the thing that's kind of fun with recursion is you can learn some small little behaviors you can really make. You can really implement some small behaviors to your advantage. So for example, if I were to do 1, 2, 3, 4, and I was to add it to 1, 2, 3, 4, let's take a look at what that looks like. Okay, so when I add two lists together, I actually get just a new list. It's a third separate object that includes all the respective elements of the things I wanted to add together. So doing addition with lists just results in a new list with all the elements in it, which is perfect. That's actually what I want. So that's a good thing. Because the thing that's difficult, though, is what happens if I do this? If I were to add lists that are of different dimensions, so this is a one-dimension list, and this is a list that's got 2 layers, because the third element has itself a list. So basically what we want to do, for any time we have lists contained in, anytime we have elements that are lists, we want to pull them out to be flattened lists themselves, so that we can just easily add together our lists. So what this actually means is, so if I were to go back to my instructions I started, so if yes, okay, so base case, is there anything left to process? Division, is this element a list or a tuple? We basically, in the repetition process, we basically want to go to the point where there is no longer any elements that are themselves lists or tuples. Because what we're going to do is we're going to pull out all of these lists and tuples into a flattened array, and we're going to return it as an array back to the previous method call that called it, and we're going to add them together as lists. If the element we're processing is not a list, we can easily just add this element to our original list, this new list in the first method call that we're going to end up returning. So this one's a little bit more verbose and probably not as straightforward. So let's kind of look at the solution now. So I'm going to comment this guy out, and let me see if people have questions. Okay, we look good. All right. Hopefully this is big enough, but if not, just let me know and I'll try to make it bigger. Okay, cool. So the original idea, we need to have just one flattened list that's going to contain everything. So let's go ahead and start by initializing that. So remember how I said some recursive algorithms, like maybe they need to be seeded with a value? This is not exactly what I meant. We'll see that in Fibonacci. So that's not exactly what I meant here. But in this case here, we just need one container that's going to end up holding all of the unique elements from all the various lists and lists of lists that we have in the thing we're processing. So pretty straightforward. This is kind of like our base case. It acts like it because basically we just need to process everything. As long as there's nothing else to process, we're going to be done. That's it, whatever. This is kind of the base case. The division part happens here. So we need to divide the problem up. And then this is going to be our evaluation steps. Okay, so let's kind of talk about this. So let's say I'm doing, let's say I'm passing this same value in. And again, just to make sure that this test case works, I ran the code and it works. So that's great. So let's reverse engineer this and understand what's kind of happening here. Okay, cool. So we'll start. We create the original, the new original flattened list that's going to be the final thing returned. I am really sorry about my mail client. I wonder, bear with me for a moment. I have Do Not Disturb. I wonder if there's a sound I can do on it. Okay, I'm not going to worry about that. Anyways, okay, so we have our original list that we're going to flatten, and let's go ahead and start processing. So for each item for each value in our items, we say, hey, is the thing that we're processing, is the current element we're looking at, is it of type list or tuple? So we're going to go ahead with this. We need to divide the problem up because we know what to do when it's just a normal element that's non-scalar that can't be divided up. We don't, however, exactly know what to do when we have something like this because we need to flatten it out, right? That's what flattening is. So this is going to be our division process. Remember that question, keep dividing the problem, like how do we know the problem is simple enough to solve? Well, this is one way. We know what it means to flatten when we have a flattened element. Oh, we don't know exactly what that means when we don't have when we have a list of lists. That's a little bit more complicated and can't yet be directly solved. So we ask this first question, hey, does this, is the thing a list or not? So for element 1, no, it's not. So we're going to execute the else block. So what we'll do, we're just going to go ahead and we're just going to append this value into our new flattened list. So that's method call 1. Method call 2, same thing. We just go ahead, we execute the else, we push it in. All right, method call 3. This gets a little interesting. So this is indeed a list. So what are we going to do? We're going to make a recursive call. So we pass in 3, 4, 5, and what happens? Okay, so here's the division process. So with palindrome, the idea of dividing the problem in was just saying let's chop off the first and the last element. Well, in this case, the division here means we're only needing to apply. We only need to apply additional instructions when we have something that requires additional work to be flattened. So that's how we kind of know. We know with lists, if it's a list, it has an additional layer of flattening that we have to do. So that's our division. So okay, so flattened is, remember, that's our original guy. So let's not really worry about this right now. Let's look at the right-hand side of this operation. Recursive flatten. Okay, so the val that we pass in, again, that's the current element we're processing. So it's going to be list 3, 4, 5. So we come in here, and now we're iterating over 3, 4, 5. We've got this flattened array here. So we do create that again when we make the first time we execute a recursive call. So that's method call 4. Yeah. I'm sorry, this is actually method call because the first time we just process a string list 3, 4, 5. List that has just one element, 5. So the 3, 4, 5 is being processed. What happens to 3 and 4? We stick them into a flattened list. And what about 5? 5's a list again. And this is where things get more interesting. So 3, 4, 5 have been processed. Let's see if we can do this. So we have method call 1, which currently just has 1 and 2. Now we've started method call 2, which has 3, 4, 5. And actually, let's say, okay, this is the value of flattened as we're processing. Okay, so method call 2 is still doing work, so method call 1 is not yet done. So method call 2, 3, 4, now we have element 5 here, which is itself a list. We're going to have to do more work, so that's going to require us to go ahead and make another method call. Okay, so now our list is equal to 5. So for value in items, is this indeed a list or a tuple? No, it isn't. If it isn't, we can just pop it in to our flattened list and return it. So basically, this is kind of the same idea, right? We've processed everything. There's nothing else to process. There's no way that we can keep going around in circles. So our fifth element, or I'm sorry, our element of value 5, that is the second element in list 3, 4, 5, which is part of the third element in 1, 2 list containing 3, 4, list of 5. It's a little difficult to say. So once we've reached this third method call, we've processed it into a flattened array. And that flattened array is pretty much just, you know, it's pretty much the same value that we stuck in. So not much magic, but how does this help us? Okay, so when we return the flattened array, notice what happens to the recursive call. You add the result of the recursive call to flattened. So remember, last in, first out, method call 3 has been finished. We've evaluated it. We've returned this flattened array. So line 34 is going to return a result of it's going to return a result of this. So this is going to say our flattened list of 3, 4, 5. We're just going to add flattened list of 5. And as we all saw, when we do addition with lists, 3, 4, 5 is actually just going to be a new list, a new flattened list with the elements 3, 4, 5. Okay, great. So have we processed everything in the original value that was passed in for the second method call? The original value passed in for the second method call is 3, 4, third element being a list. Yes, we have. We've just done the recursive call that took care of the third element. So our value of flattened is 3, 4, 5. So let's go ahead and just return that. We're going to just return this value back to method call 1. So 3, 4, 5 now is going to be the result of the recursive call. So 1, 2 is pretty much the math that we do. 1, 2 plus 3, 4, 5. And what do we get? We get 1, 2, 3, 4, 5. So what you can kind of see is there does not need to always be a recursive call for every value you're processing. That's kind of why when we started a little while ago and I said, well, what's the base case? How does that look? That's going to change depending on what problem you're trying to solve. Again, the idea for kind of mapping this out, you want to ask yourself, you know, what's the goal I'm trying to solve? once I have that goal, how do I make that, once I understand what the goal is there a way of representing that problem in a simpler form? So the idea of a palindrome can be reduced into saying, are each pairs of characters the same? For our flatten method, we can say, okay, what I need to do is flatten this. That's great. That's my goal. But instead, what you can say is, I know by flattening, it's either, hey, I'm going to add an element in, or I'm going to have to process each element to the point where the final thing I'm processing is itself just contained of elements, of just non-lists. That's the best way of saying it. So that base case is a little bit more complex. But again, the way of simplifying the problem is we know what to do when we have the list of just numbers. We don't know what to do when we have a list of lists. So we just need to keep reducing the thing we're processing until we get to the point where we only have the directions we know what to do, which is line 36, flatten plus append a val. Or the other thing that we have available, which is we know that when you add two arrays together, it results in a new flattened array. So, I'm sorry, not array, list. So yeah, this one's a little bit more involved. But again, if you can go through the method calls and see the behavior, it's going to help illuminate a little bit. Okay, cool. So that's the flattened list. So for those of you who like math, Fibonacci is a really classic example and a really good one. And actually, there's two different ways I wrote the recursive call. So let's pop back into the room, see if there's questions. Okay, we look good. All right. I believe the font size is good for everyone, so I'm just going to go ahead and move back into this. So again, let me know if things don't look the best. Okay, so great. Fibonacci. So one thing you should know about Fibonacci, and anytime I do Fibonacci stuff, I always have to remember what the definition is. All right, Fibonacci is formed by adding the last two numbers to get the next one. Here's a big thing that is going to help us. Fibonacci series always starts with the values 0 and 1. So the idea of Fibonacci is, you can see this guy here. This is Fibonacci sequence. So the idea is the next value in your series is going to be the sum of the previous two numbers. So 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3, etc., etc. And just for the sake of what it means when we say, give me the first Fibonacci number, the first Fibonacci number is value 1. It is not 0. That's going to be the 0th Fibonacci number. So the 5th Fibonacci number will be 5, the 11th will be 89, etc., etc. So we can kind of use this. We can kind of use this to help guide us. Okay, cool. Any questions on Fibonacci? Does that make sense? Okay, I don't see any. So let's go back to it. All right, so we know Fibonacci always starts with 0 and 1. So that's why we've got this here. So if we were to think about Fibonacci, questions I may use for how to break a problem down. What is Fibonacci? How can we divide the problem? What is the base case? So actually, when I first start doing problems, if a thinking recursively takes some time, I tend to actually write iterative solutions, just because this may not become apparent until I've actually started understanding what the redundancy is, what the repetition itself is. So we've answered question 1. What is Fibonacci? Now, how do we divide the problem? I'm not exactly sure yet. Let's go through an iterative solution, see what we learn, and then maybe we can answer questions 2 and 3. Okay. So Fibonacci, awesome. All right. So this is kind of a first stab at a Fibonacci solution. You can write this a few ways, but one thing I can think of, and I tend to get list happy, is kind of like what we saw in the notes on Fibonacci. Fibonacci is, a stream of numbers, so maybe that's how I want to represent Fibonacci. I want to represent it not per se as a stream, but as a sequence. So I'm going to use a list to seed my initial values. So Fibonacci, we start with 0 and 1. So the goal of this method here, I'm basically going to ask, you know, what is I want to say, hey, what is the 8th Fibonacci value? So if I ask for 8, I should be able to say that I get 21. If I ask for 11, I should get 89. So again, if I ask for 0, that's going to be 0. Okay. So Fibonacci sequence, I have my initial values. Those are always required to start the sequence. All right. So if I'm saying, if my goal is to find the, I've got 11 here, to find the 11th Fibonacci, how do I get there? Well, first thing is basically I need my pattern. The pattern all the time is going to be the next value in the Fibonacci is going to be the sum of the previous 2 numbers in the sequence. So I've got to have that in there. That is pretty much the pattern that is driving this whole sequence. Now, how do I know that I found that number? Okay, well, this is a little quirky. This line might seem a little awkward, but basically what I want to know is, have I done, X number of operations to get to the 11th value? The thing that makes this a little interesting is because 0, the first Fibonacci isn't considered the first until you have value 1, but yet the sequence always includes 0 and 1. So it's kind of, it might be akin to you thinking of how arrays are 0 or how lists are 0-based. We can kind of think of Fibonacci as being 0-based. So there is a little bit of an adjustment here. So when I say num, I need to understand that that the 0 Fibonacci is going to be 0. So the one way I can kind of have a terminating, a way to terminate the construction of Fibonacci values is I can say, hey, is the length of the Fibonacci sequence not equal to num plus 1, so the 12th, because 0 is going to be included in my sequence. So long as I haven't reached the 12, so long as my sequence is not equal to 12, then I know I need to keep generating Fibonacci sequences. So this is a little bit of a crude mechanism, but it works, right? The adjustment here for num plus 1, because my array or my list has to include 0. So that's going to bump the length up a little bit. So let's run through this. While the number of Fibonacci's calculated is not equal to the value I'm looking to, go ahead and just keep applying this pattern of adding the values of the last 2 sequences together to create my new one. Once I've reached the number that I'm looking for, return the last value calculated. So if I were to just go ahead and execute this, notice how quickly this gets very big. 11 does indeed equal 89, and 35, 9227465. And as a fact check, let's take a look at 35, 9227465. So I look pretty good. Okay. So what are some insights I learned from this problem? Well, base case, maybe there's something to be said about keeping track of how many sequences I've generated, how many numbers I've generated in the sequence, and see if that's equal to the number I'm looking for. Because that's going to be a way that I know that I can directly solve this problem. I just have to keep track of how many Fibonacci's values I've generated. And then the idea of dividing this problem, well, simply put, it's just doing this. It's just repeating the process of adding the last 2 sequences together. So the problem is not looking at it in its entirety and trying to understand how to generate all values at once, but instead generating values as we go. Okay, so let's refactor this a little bit, and let's try doing this recursively. Okay. All right. This is seeding values. So back to the idea of creating an algorithm, a recursive algorithm, where we said we may have to seed some values. I'm not sure what slide that is. Oh, okay, slide 20. So initialize the algorithm. Recursive programs may need a starting value. The starting value, I'm going to be making use of I'm going to be seeding an initial value for 0 and 1, because that's always required for the Fibonacci sequence to be created. And actually, you know what? I just saw some questions, so let's pop in here. Okay, great. That's not a okay, great. That's not so much a question as much as where are we at? Okay, so recursive Fibonacci 1. So this is going to be a little different perhaps than what we saw before when we used recursion. We did not start with any preset values. Well, in this case, I'm going to actually seed some initial values because for the first time that I make this recursive call, I need to start with some values. It's just the way Fibonacci works. It requires 0 and 1 to start the sequence. So back to our base case. So line 11 in the iterative solution, we can translate into the base case on line 20 and 21. If the length of the sequence, and again, remember we've got that adjustment because Fibonacci 0 is going to be 0. So the number is going to kind of be adjusted by 1. Since we're using that, we're using a list to track the values. So when we say here, you know, so long as we've reached the point that we need to calculate, that's going to be our base case. We're keeping track of how many values we've created. Okay, so if the length of the sequence is equal to, you know, the 0th Fibonacci plus the number of things we've calculated, let's return the last thing in the last value we've generated. So that's our base case. And here's the simplified problem, which is basically just keep on adding to the previous 2 values that we've calculated to make the next value that's going to be in our sequence. So this is going to be the replication. This is going to be the repetition process. This is our base case. And this is our recursive call. So very cool. So this is kind of the, you know, the evaluation. Sorry, it's a repetition. This is our repetition, the Fibonacci call. So we come in, we say, okay, cool, let's do Fibonacci 5. All right, so Fibonacci 5 should return 5. We come in, we say, hey, is the length of the number of the values I've created equal to 6? Because again, we include 0, which is Fibonacci 0. No, it is not. We're going to go ahead and say, all right, 0 plus 1, that's going to be 1. So now we've updated our sequence to be 0, 1, 1. And we go ahead and we pass that value sequence in as the new sequence. And we keep num the same because we need the num to continue to evaluate how many times we've run through these instructions. Next time around, is length of sequence equal to num plus 1? Nope, we have not yet hit 6. So let's go ahead and do this. 0, 1, 1, 2. Let's make the recursive call again. Is length of sequence, which is now 4, is that equal to 6? No, it is not. Let's go ahead and add the last 2 values. We get 3. Is length of sequence, which is now 5, equal to 6? No, it is not. Let's add the last 2. 3 plus 2 is 5. And let's make the recursive call one last time. Is the length of the sequence now equal to 6? Indeed it is. So let's return this last guy. So 5, is 5 equal to 5? Yep, we've got what we wanted. So let's, just for sanity, check some more. All right, we've got all trues. And because I like to double check, 35, 922, 7465. 722, 922, 76. We look good. So 11 is 89, etc., etc. So we're pretty much kind of doing the same thing as we did in the while loop, except rather than using the while loop to power the call, we're instead using the recursive call to execute this set of instructions over and over, line 12. And then every time we're asking, hey, should we stop? Should we stop? No, we shouldn't. Keep going. Okay, cool. So yeah, this is not that much different, and we do seed some initial values to drive this recursive solution home. Okay, so that's good and dandy. Can we do more for this? Okay. All right, let's look at this. And recursive solution number 2. All right, so this one's kind of interesting. And this is, if you were to look around for recursive solutions, this will most likely be the one that you find. So perhaps something we haven't seen before, where we're adding together the results of 2 recursive calls, not just 1 recursive call. So let's take a look at this. Okay, so before we were saying, all right, our base case was, have we done all the number of calculations we require? Does the length of all the things we've calculated equal how many, the number of calculations we want to find plus that Fibonacci is 0? In this case, our base case is going to be, is num equal to 1 or num equal to 2? If so, return 1. And so I wonder what this means. So let's take a look at that. So if we were to look at, if num equals 1 or num equals 2, you actually look in the first 300 Fibonacci numbers, num is value 1, or the first Fibonacci number is 1, the second Fibonacci number is 1. So this is actually what this is returning to. Our base case, again, it's going to be, the base case here is essentially we're saying, hey, let's reach the end of the Fibonacci, where you can't go the Fibonacci sequence, you can't go past 1, right? 0 is going to be 0, and there's nothing before 0. So we're basically saying, okay, cool, these values are the same. So if you get to a point where num is equal to 1 or num is equal to 2, we've reached the end of the Fibonacci sequence. We can't do any more work. So rather than us generating our values left to right, we can think of generating the values right to left. And how do we do this? Well, this is kind of nifty. We know the pattern essentially is each value is going to be the sum of the previous 2 values in Fibonacci. That's pretty much how the pattern works to generate your next values. So we can actually try putting this pattern in directly to num minus 1, num minus 2, which would mean the previous Fibonacci value and the second previous Fibonacci values. If we could actually find the values of those 2 guys and add those together, then we can actually find the value of whatever number we're looking for. Because the pattern for Fibonacci is always going to be the sum of the previous 2 Fibonacci values. That's pretty much what we're doing here. We're just representing num minus 1, num minus 2, and then our formula for doing this, what is our formula for doing this? Well, let's take a look at it. So let's start with a small number, 5. So num minus 1, that's going to give us 4, and num minus 2 is going to give us 3. So if we were to follow this call stack down, num minus 1, I'm going to kind of try to take some notes down here. So num minus 1, we've got 4. So is 4 equal to 1 or is 4 equal to 2? Return 1. Nope, we don't have that. So num minus 1 is going to then be recursive call. So when we come in, we then have for value 4, we say num minus 1 is the sum of num minus 1 is going to be 3, and num minus 2 is 1. So just kind of see what's going on here. We're each time for each value, we're splitting it up. We start on method call 1 with 4 and 5 minus 2 is 3. So I'm now going to, if I do the tracing down on the left-hand side, we keep splitting this problem up into 2. So you can kind of think of a tree a little bit. If you've ever seen the way a binary tree structure works, you subsequently break the problem for each value 2 times more. So the number of calculations is going to exponentially grow. So for 3, and just for the calculation for 4, is going to be Fibonacci of, it's going to pass in the value 3 and the pass in the value 1. And right away, this is going to kind of, if we were to trace the num minus 2, which originally we had 4 from the left-hand side of looking for the 5th value. If I had 1, and we've traced that back down, so let's say I'm tracing the right-hand side. So 1 minus 1 is 0. Actually, we don't even hit that step because we say if num equals 1 or num equals 2, return 1. So this is just going to right away return 1 for us. 3, if we were to trace that down, num minus 1 is 2, and 3 minus 2 is 1. We know that's going to return 1. But granted, we don't hit that point because remember, base case comes first. So if we pass the value 3 in, we have 2 minus 1 and num minus 1. So 3 minus 2 is, so we have 2 and 1. If we were to process that down further, for, let's say 1, pass in if num equals 1, so we know that returns 1. And for 2, if we were to pass in 2, we know that returns 1. So basically what we're kind of doing, if you were to continue to do this, continue to follow all these paths down to its culminating point, is we basically drill down the Fibonacci all the way down to this base case of 1. So you'll eventually have all these 1s that add up. So you'll have 5 values of 1. So it'll be 1 plus 1 plus 1 plus 1 plus 1 equals 5. So it's this one's a little bit more complicated because you're doing more recursive calls at a time. But essentially, the only thing that you do know, the way that you're kind of designing this one is you're saying the only thing that I do know is that the sequence is that the first and the second values are 1. I'm going to reduce the problem down until I get to that point, and I'm going to add up all the values together to essentially get to the point. I'm going to reduce down to the point where we have that base case of 1, and once I've processed everything to that base case, I'm then going to add up all the number of 1s I have. So in the case of 5, it'll be 5 times we've reached the base case of 1s, well, I'll just add those all together, and that would be 5. So this one's probably, for me, when I look at this one was not as intuitive. How I started, when I started looking at doing recursive solutions, this one was a little bit more straightforward. Rather than making the problem going kind of top down, it was more sensical for me to go from the bottom, for going down up, I guess, if you will. So, you can see that recursion can come in multiple kind of formats, and some of it may be a little bit more difficult to trace, particularly when you have multiple method calls happening simultaneously. And this one's a little bit more straightforward, correct? But the idea is always the same. You need to have some base case. You need a way to have some evaluation, and then a way to repeat the problem or divide the problem until it's simple enough to solve. So in this case, the way it's simple enough to solve it is that the first and the second Fibonacci values are always going to be 1. Okay, cool. So I think, okay, cool. So that is that. So let's go ahead and pop into our last problem. Okay, so for those of you who have seen binary search, this is a really good one and can be solved quite a few ways. But the idea of binary search, there are some conditions here. So the idea is you always require a sorted sequence. So in our case, we're going to have ascending order. We always require that whatever value that we're trying to find that whatever list that we're trying to find the value in, it needs to be sorted. It requires that things be, in this case, we're just going to say in ascending order. So our goal is just to basically find out if a value is present in a sorted list, yes or no. So what does that look like? Okay, cool. Binary search. Okay, so binary search. All right. Basically, my end goal is I'm either going to say true, something's present, or false, it isn't. And how can I go about doing that? Well, binary search, there's actually an algorithm that exists, so I don't have to come up with these instructions myself. Basically, binary search says take the midpoint of your list, ask the question, is the midpoint equal to the value I'm looking for? If it is, return true. If the midpoint is greater than the value I'm looking for, then basically move the midpoint to be the upper threshold of the value I'm looking at, and only look for the value I'm looking for from 0 up to the original midpoint. So basically, I'm going to be halving the size of the array I'm looking, or the half the size of the list I'm looking through each time to find the value I'm looking for. So let's and then vice versa. If the value if the value I'm searching for is not is indeed greater than the midpoint, then we know that the value I'm looking for is going to be in the range of the original list from the midpoint up to the end of that list. So let's break this down a little bit. Okay, and again, because I like to just do this. Okay, I have two test cases. So 2, do I expect it to be in my list? Indeed, that's true. 6, is 6 present in my list? No, it is not, so I expect false. So let's start with our first test case. Okay, cool. All right, so each time we go through, the idea here, our end goal is always going to be, you know, how can I culminate and know that I've done everything I need to do? And what's the case basically that I hit that my value is indeed not in my list? Well, if the lowest value in your list is greater than the highest value in your list, then you know that you've looked at everything in your possible list, and indeed it's not present. That might sound a little awkward, but we'll look at that in a second. And then the way we know that we can totally be done is if indeed we do find that whatever midpoint we're looking at is present to the value we're looking at. Okay, cool. So the way we know that we're done, either the value matches when we grab a midpoint, or we've processed everything in here and nothing in here is indeed equal to the value I'm trying to find. That's kind of what this condition is saying. So let's go ahead and start this. Okay, so binary search says start by looking at the entire thing, grab a midpoint, determine if the midpoint is higher in value or less in value than the thing you're looking for. Why do we do this? Because we can use that midpoint. Again, that's why we have the assumption that this is a sorted list. If this is indeed sorted, we can then say, well, if the midpoint is greater or less than the thing I'm looking for, I can make a decision as to what part of the list I should process next. If the value of the midpoint is greater than the value I'm looking for, then I know I should process the smaller values. If the midpoint is indeed less than the value I'm looking for, then that means I should process only the right part of my original list. That means the higher values, because again, this is sorted. So that's kind of the logic driving this behind. So if we ever reach the point where low is less than high, low we start with as the first element, and high we start as the last element. That is, if we ever have anything where this value low is kind of always going to be changing, we reset it as we decide which direction of the list to process, the right or the left side. If we ever get to the point where low is greater than high, that let's say 5 is high still, and somehow low, we've gone through each of these elements, we've processed each section of the list, and now low is 6. That's outside of our range. That does us no good. So that's what this is essentially saying. Okay, cool. So let's actually go through and do some of this computation. So low will be 0. Mid, our midpoint is going to be the length of our list divided by 2. So in this case, we have 3, 6. So that's going to be 3. And then high is going to be length of list. So we have 6. And we say, okay, is low less than high? Well, it is. That is indeed true. So what does that mean? Okay, well, let's go ahead and do some calculations. So this double divider is floor division. So when you do division, you're going to get you'll get a whole number, but you're going to get the lower. You'll round down rather than rounding up. So that's what this operator does. So mid equals low plus high divided by 2. We've kind of already done that. Whatever. but mid is basically going to be 3. So we know that. So it is the third element in our list is 0, 1, 2, 3. Is that value equal to the value we're looking for? So is 3 equal to 2? No, it is not. Is 3 greater than 2? Yes, it is. So 17 is going to evaluate as true. So we reset the highest range that we're going to be looking at as the original midpoint, because we've made the decision that it's only because this is a sorted list and the original midpoint of the list is greater than the value we're looking for. And there's no way that it can possibly be in the right-hand part of our list. So we reset high as being 0, 1, 2, 3 as being the third element. And then we say, okay, cool, let's go ahead and repeat this process. So mid, low plus high, so 0 plus 3 divided by 2 will get us 0 plus 3 divided by 2. It's going to get us 1, so 0, 1. It's going to be our midpoint. We'll ask the question, is this equal to the value I'm looking for? No, it is not. Is the value that I'm looking for, is the mid greater than the value I'm looking for? No, it is not. So we know then that it can only be in the right-hand part of the list, not the left-hand part of the list, because again, the midpoint is less than the value I'm looking for. So now we're processing 1, 2, 3. So now that we're down to 1, 2, 3, let's see. So while low is less than high, so low is 1, 2, 3. Low is still 0, so we're good. And high is, let's see, or actually, I'm sorry, low is mid plus 1. So low is 1 plus 1, so we get 2. So low is equal to 2, and high is still equal to 3. So is the second index less than the third index? Yes, it is. Midpoint, let's add these together, divided by 2. Zero, 1, 2. And then we ask the question, is the midpoint equal to the value I'm looking for? 0, 1, 2. 2 is indeed equal to 2. So the way that the binary search works, we basically pick a midpoint. We know this is sorted. We say, hey, if it's not equal to the value I'm looking for, then I'm going to process the right part of the list. If it's not equal to, if the midpoint is indeed greater than the value I'm looking at, then I'm going to process the left part of the list. So basically, rather than searching through the entire thing each time, we're only going to look at we look at increasingly smaller halves of the original list. We start with the whole thing, then we have, and then we have, and we have, until we get to the points. If you've gotten to the point where the low has been reset to a value that is greater than the greatest value in the, or than the greatest, if you get to the point where low is greater than the number of elements in your list, then you know you've gone through everything and is indeed not there. So it's kind of interesting because rather than processing the whole thing at a time, you just process components of it, and this is actually a pretty quick implementation. So the iterative solution, we see a possible base case here where we actually get the value we want, or a possible base case here. We've processed everything and we know we can no longer process. And the repetition, or the way we can divide the problem, kind of comes through this. We do a quick check. So this is going to be our evaluation. So base case, low less than high. Evaluation, line 15. Is the value indeed equal to the thing we want? And then how do we break up the problem? We either make a decision to go right or we make a decision to go left. It's pretty much as simple as that. And depending on going right or left, you're going to have to update the markers that point to high. You're going to have to update the markers for what constitutes the lower or the upper component of the list you're looking through. Okay, so that is iterative. So how can we retool this for recursive? Alrighty, let's take a look at this. Okay, So recursive binary search. All right. So this looks a little different. Is the length of the list equal to 0? So let's think about that. If our original base case was, is low less than high, basically that's saying, hey, is there anything left to process? This is pretty much the same thing. Is the length of the list, is there anything we can process in the list? That's basically us refactoring that, that condition to work in how we're going to process the binary and how we're going to process binary search recursively. So this base condition is still asking the same thing. Is there anything left to process? If there isn't, we know we failed and there's nothing there. So recursively, so kind of like what we did with the palindrome, where we kept reducing the size of the problem, we're going to do the same thing here. Rather than us using a while loop and just kind of looking over the same list with different pointers, we're going to be doing that. We're going to have different pointers by actually passing in either smaller portions that are on the right hand or the left hand side of the original list. So in the case that we do, so 0, 1, 2, 3, 4, 5, we know that the midpoint starts as 3. Is here's our other possibility for a base case by saying, hey, evaluation, is this true? If so, we're done. Or else we or else our decision is going to be, okay, cool, let's just look through a smaller component in the list. If the value that we're looking for, if 2 is less than the midpoint, 2 less than the midpoint, that is indeed correct. Notice what we do here. Recursive solution. We're not passing in the entire list. We're only passing in this portion of the list. 0 up to 3. And then we process that and we say, okay, cool, what's the midpoint? We know we get 1. Once we get 1, we can say, hey, is 1 less than 2 or is 2 greater than 1? We know 2 is indeed greater than 1, so we're going to execute this part. Line 40. So for line 40, we're going to go ahead and process 2 and 3. The midpoint we get this time is going to be 2, which indeed matches one of our base cases. Is the midpoint indeed equal to the value we're looking for? In the case where you don't have an item in there, basically you're going to be just passing in a subset of the list until there's nothing left. There's no subset left to be passed in which case you're just going to return a false. So the thing about this solution that I think makes it a little bit more intuitive for us is, rather than us having to kind of keep track of all the pointers and know where we are in the list, we actually just know that we're reducing the size of the list that we have to search through. The pointers are still only looking through a subset in the list, but I personally think that trying to do the math and keep track of where all the pointers are is a little bit more confusing. Here, it's very intuitive. We know, hey, the list is only going to be 0 up to whatever the new endpoint is, and the endpoint is determined based on the new subset you pass in. So basically, the simplification here that we see is, well, hey, why do we care about pointers? Let's just pass in let's just make a new list. We get the midpoint, and from that, we either say, hey, we have to continue searching, or no, we don't, because we've done all the searching we can, or it's actually a match. So that is the recursive binary search. Granted, you can write this a few different ways. So kind of like with Fibonacci, where maybe you can make use of some initial seeded values, or you perhaps use different data structures, like in this case we had a list to represent all the sequences. Binary search, you can also write a few ways. Perhaps I could have an optional parameter, which is the midpoint, and I pass that around as well. And I seed the initial midpoint to be the value of a list.length divided by 2. So there's obviously a few different ways you can write these things, but the core consideration and what's really important is you really need to understand what is the pattern that's being applied and how do you break out of the pattern. Because if you don't have a way to break out of the pattern, what can happen, you'll get basically you'll run the program, it will hang. You'll notice on your activity monitor, if you're a Mac user, this is awesome. You'll notice one of your processes going crazy. It's using a lot of gig, and it's because, like a while loop where you can have an infinite while loop, the recursive call is continuously recursing and has no way of reaching reaching an end. So you have an endless recursive call stack going on. So base case is instrumental. So these are just some of the few beginner problems for recursion. Another classic one that I think is pretty easy to try to implement is doing factorial. That's a really easy one where you have find the factorial of 8, which would be the multiplication of 1 times 2 times 3 times 4. It's basically 1 up to n. So you could find that pattern and try to figure out, okay, what is the pattern? The pattern is, what is that pattern, and then how do I represent that, and then how do I break out of the pattern? When do I know I've reached the end of it? Which in this case, Fibonacci, we know we've reached the end of our pattern when we have num equals, the number we're looking for is 1 or 2, because it's always going to be equal to 1. That idea that the sequence always starts with 0 and 1, that's the point of either start or end, depending on if you're going top down or bottom up. So that is kind of a few different recursion problems. And I think the big thing, now that we've talked a little bit about, what is recursion and how does it look, why would we actually want to use this? Okay, I've got there's some things I think I've been pointing out here. Recursive problems, as we've seen, we can definitely use iteration to solve it. But when some of the advantages, perhaps, of using recursion is recursion can remove some complexity. So, for example, the idea of Fibonacci, this can be it can be a little difficult to kind of keep track in your head what number you're on, because you have to, perhaps, for example, you could start by saying I need to generate all the values. Starting with 0, 1, and perhaps that seems more complex. Or you can say, I know that the pattern is always going to be the sum, that the next value is always going to be the sum of the previous 2 values. So if I can generate them down to the point where I know the pattern starts, then I can apply the simplified pattern and allow the call stack to compute that. Or maybe a little bit more of an easier example, if recursion's removing complexity, one way we can think of it is the palindrome problem. Rather than thinking of the word the entirety of the word, we can think of the word as just being combinations of these pairs. And that really is the pattern, right? Is the nth letter equal to the negative nth letter? Recursion is going to just focus on this simple pattern and continue to apply it, allowing the call stack to reach a point where it can actually make that, the decision to evaluate, or it makes the decision to keep going forward. So that's one thing. Recursion can remove some complexity. Another thing, perhaps it's easier to understand. It does, I definitely think, take time to understand how recursion works, but once you look at it, you kind of can pick some things up right away. So I think for me, a binary search, like what I was saying earlier, right away I know that, hey, I've got a midpoint. Cool. Okay, I'm going to be slicing this. I'm going to be slicing the list up into the point it's either there's nothing left to slice and the value is not present, or hey, the thing that I'm looking for is actually indeed in the slice that I've passed in. So to me, this is a little bit more intuitive, whereas perhaps for this, trying to keep track of all these operations and the shifting pointers of low and high can be a little bit more complex. Or even in the flatten, back to the idea of having nested for loops. For loops, nested for loops can be tricky to keep in the back of your mind, whereas maybe the argument here is pretty intuitive, where you're saying, hey, keep flattening to the point where you have either an element to add to the list, or I've pulled all the elements out into just one flattened list that I can add to a previous flattened list. Pretty direct. It's just basically just 2 methods of adding items to a new list. It's either you're adding new lists together to make a third new list, or you're just adding to the existing list an element. So that seems a little bit more intuitive. And then, why use recursion? 3, if there's multiple layers, recursion can make this process simpler. So imagine trying to iteratively solve how to flatten a list. Think about how many times you might have to write nested for loops. That can get a little sticky. The while is definitely one way of doing it, but it can take you a little bit of time of thinking about how to implement that. If you're able to see a pattern and you can abstract that problem down to the point where that pattern can be applied and you can evaluate, it allows the code to be more, a little bit easier to read, allows the call stack to handle the various layers of calculations, and simply put, it makes understanding the procedure easier to follow. And maybe this is just my personal take on it, but I think knowing how to do recursion can make you feel like a superhuman. Or, I think also understanding how to apply recursion, it really allows you to think about, it really allows you to get into the process of abstraction and understanding how to take a complicated process and distill it down to its essence. And that's really what programming is. Yeah, we're always trying to abstract processes into, into a series of subtasks, and that's at heart what recursion is. So if you're looking for more resources, because definitely this is a very, very small talk into a more advanced algorithm design type. There's some resources here that I've listed. So the Stanford CS 106, they've got a discussion. They have a lecture that's recorded about 45 minutes talking about abstractions, and then also they've got a very easy to read overview on recursion. Interactive Python, I think, is beautiful. Particularly if you're looking to understand, so if we can do recursion with binary search, you can make different sorting algorithms you can rewrite as an iterative and a recursive solution. And Interactive Python has a beautiful discussion on different sort algorithms as well as on recursion itself. So I think that one's really great. And then of course your local Python user group. You can go check it out on the PSF, see what group is in your area, and look for resources. Meetup.com is a beautiful place, and of course, PyLadies Remote, because they are great, and we want to make sure we continue to create content for you. So here's a fun fact: I have yet to use recursion professionally, and it is something that I don't know if I would use professionally. Perhaps if I'm sure someone somewhere, maybe I'm in web development. Maybe not in that realm do I have to use recursion. I'm sure someone somewhere has to use it. But for those of you who still are working through this concept, it is something that I've yet not had to use. But it is, I think, a really good tactic to have a good tool to have in your tool belt. So that is pretty much the class. I really appreciate you being present, and thank you so much for our TAs for being helpful and answering questions and hopefully pointing to resources. The last bit I would just ask for is if you have any feedback or suggestions, please reach out. I am very present on Twitter. Make pull requests if you want to add more problems to the repository on github.com. But that is where we are at, so maybe we can come back and do another recursion class in the future, so I really appreciate it. Apart from that, I think we look good. I don't see any terrible questions in here, and it looks like Lauren's been great helping out with questions. But if you do have anything else, please feel free to tweet me or tweet PyLadies Remote. They will be able to help with any questions, and we can see about getting answers into your hands. But that being said, the good thing about this class, about this Google Air, wherever I put you, is it is recorded, so we can share this with everyone. Okay, beautiful. There we go. That's where I put it. Okay, so I will go ahead and actually share this, and I'll if you have any more suggestions for resources, let me know. But I appreciate you all being here. So I'm going to go ahead and wrap up today's class, and you all have a good rest of your Sunday.